In this lesson, we'll be learning how to factor to solve polynomials. So our objective today will be to learn different methods to factor polynomials and to solve polynomials by factoring. Let's just review something very quickly. When we were dealing with quadratics, we factored them. Factoring was one method of solving a quadratic. So if we had a quadratic like this, what we would do is we would factor it. In this case, it's easily factorable. And then we set either of these two terms to 0. And when x is equal to 7, or in this case, x is equal to 1, we have a solution. This is how we solve quadratics by factoring. And so what we want to do is we want to extend this same idea to polynomials as well. When we have a polynomial equation, we can also solve it by factoring. So here's an example. We have a larger polynomial here. And in this case, I'm just going to factor it. We'll learn how to factor it in a bit, but just say that we can factor it down to this. If we factor it down to this, we do the same type of thing where we set each of these three terms to 0, and so then our solution in this case can be -2, 3/2, or -3/2. So the concept is still very much the same, where we take this, set it to 0, take this, set it to 0, or take this, set it to 0, and now any one of these three terms here will be our solution to this polynomial equation. So the key is, if we can factor, then it's going to be very easy to solve the polynomial equation. So the rest of this lesson is all about how do we factor polynomials. So when we factor polynomials, there are actually 4 different methods that we're going to be looking at, and it's a little bit of a challenge where we have to figure out which one of the methods to apply. It's not always obvious, but there's some things that we can look at that will help us. Let's start with a definition. For a polynomial to be completely factored, it means that we can no longer continue factoring with integer coefficients. There's nothing else we can do. So let's look at the 4 methods right now. We have the common factor method, the special pattern method, grouping method, and what we call quadratic form method. We'll look at each one of these one by one. The common factor method, we've already talked about this. Actually, this is the most important thing. Always look for common factors first. In this case, we have a polynomial, and we can look at this, and there is a common factor term. There's an x squared, there's an x in this term, there's an x term in this term, and also an x in this term. So we can factor out that x, and then we get to this point. We're not done yet. We could actually now, once we see it in this form, we can notice, we have a quadratic here, and we can actually factor this as well. This factors down to x plus 1 times x plus 2, and now we can't do anything more. Now it is completely factored. Let's look at another case. In this case, we have another polynomial, and at first glance it might look like we can't do anything, but again, look for the common factors. Not just in the variables, but also in the numbers. We have a 2, we have an 18, they're both even numbers, there's a common factor of a 2. We also have a common factor of x to the third. So we can factor out the 2x to the third term, and then we can write it like this. Now, if you have trouble getting from here to here, what you can do is think about it like this. Think about it as dividing each of these terms by 2 times x to the third, and then this becomes x squared, and this becomes -9. This isn't necessary to write out, but if you have trouble factoring it out in your head, you might want to write it out like this to get down to this form. Now again, this is not in its completely factored form because we have a difference of perfect squares. So whenever you see an x squared term here minus a number which is a perfect square, it should raise some bells in your head. We can use our pattern that we've learned before and express this as x plus 3 and x minus 3. So this actually leads us into our second method, which is special patterns. This was a special pattern which we used to realize that we can turn this into this. Before we do that, just want to make sure, always look for common factors. That's our key thing. Look for that first. Of all the methods that we're going to be learning today, always look for the common factor first. Okay, let's move on. Second method. The second method is to examine and look for special patterns. We already talked about the first kind, which is the difference of perfect squares. So if we ever see something like an x squared or a 9 or a 16, we should think, is it a difference of perfect squares? But we also have some other patterns. We have difference of cubes and we have sum of cubes. So the difference of cubes starts out kind of like the difference of squares, where we have an a cubed minus b cubed, and it's equal to a minus b, and then times this. So this is just something to try to memorize, to try to kind of put into your brain. We have a sum of cubes, which is similar to it as well. The only difference being here, this term right here and this operator right there. Those are the differences. Now, unlike difference of squares, where there's no such thing as sum of squares, we do have both the difference of cubes and the sum of cubes as a special factorable pattern. So let's see how we can use this. Let's start off with this example. We see x cubed term here, and we see 64. When we see this x cubed term, again, that should start making us think, is this 64 also a perfect cube? If it is a perfect cube, then we can apply the sum of cubes. And indeed it is. 4 to the third is equal to 64, and we can think of that as our a cubed plus b cubed. So what we can do then is we write out underneath, we can write it out our pattern, and then we just plug in the x, which is our a, and the 4, which is our b, into this pattern. So we took our x, which is x, which is a, our 4, which is b, and then again we plugged this also into the a's and b's of that special pattern. Let's look at a slightly harder version. Now in this case, this polynomial, the very first thing we do, look for the common factor. In this case, there's a common factor of x squared. So we're going to take that out first. In fact, there's another factor of 2 as well. We want to look at the numbers. Both of these are even numbers, so we can take out a 2 as well. So let's factor the 2x squared out, and we're now left with 8x cubed. And so this, again, this x cubed should alert us. Let's start looking for perfect cubes. Is 8 a perfect cube? Yes, it is. It's actually 2 to the third. Is 125 a perfect cube? Actually, it is. It's 5 to the third. So we can now rewrite this. We can write this as 2x to the third minus 5 to the third. And these are our a cubed minus b cubed. And so then we can just rewrite this using our special pattern. And I put it down below just as a template. You don't have to do this, but as you start doing it, you might want to do this just as a method. And then wherever you see the a, you put 2x. Wherever you see the b, you put 5. And we do that for the entire pattern. And then we simplify that out. And then we get to our final form. And there's nothing more we can do. This is our fully, completely factorized term here. Okay, let's move on. Special patterns. Now let's look at grouping. Grouping is another way of factoring, and the key thing to look for is look for 4 terms. If you see 4 terms, you can potentially factor them with this grouping method. And this is how it works. We look at each of these 2 terms separately. Let's look at the first term over here, first 2 terms here. Let's look at the first 2 terms over here separately. Look for common factors. In this term here, there's an x squared term in both of them. So let's write that out. Let's factor it out. In this next term here, we look for common factors again. And in this case, we have a 16, which is a common factor because 48 divided by 16 is 3. So we can write this out like this, where we factored out the 16. So we took the first pair, factored out the x squared. We took the second 2 terms and factored out the 16. And then this is what we observed. Now this isn't always the case, but when grouping works, we actually will find that there is a common term in both of them. And we see this common x plus 3 in both of them after we've factored out through this step above. So in this case, we can continue on. This tells us that grouping is a viable method for factoring the polynomial. And so then we can, in a sense, factor out the x plus 3, and then we're left with the x squared right here and the 16 right there. So this is how we factor by grouping. Let's look at one more example of this. Again, what we do is we start off by looking at the first 2 terms. There is a common x squared term here, so this we pull out this common factor. And in this case, we see a common factor of 9. 63 divided by 9 is 7. And just be careful with the negative signs here. We're factoring out a negative 9 in this case. So negative 9x divided by negative 9 is x. Negative 63 divided by negative 9 is positive 7. And in this case, again, we look to see if grouping is going to work for us. And in this case, again, it does. X plus 7 is common to both of these, so we can continue on. This grouping method will work. So we factor out the x plus 7, and we're left with an x squared term minus 9. Now, again, we're not done yet. We can recognize that this is a special pattern. This is a difference of squares, difference of perfect squares. So we can rewrite this now in a final factored form: x plus 7 times x plus 3 times x minus 3. So that's grouping. Again, the key thing is it works on 4 terms. So if you see 4 terms, maybe you can try the grouping method. You start off by factoring out and then seeing if there is a common term between them. Okay, final method. The final method is what we call the quadratic form. And what it is we start with 3 terms, and we notice that there's this pattern here where x to the 3rd, and we have x to the 6th here. 6 is twice of 3, so we can turn it into a quadratic form. So what we say here is that x to the 3rd squared, same as x to the 6th, and we have here 5 times x to the 3rd. So we can then say let y is equal to x to the 3rd. And we're going to substitute wherever we see the x cubed, we're going to substitute it with y. And so now we're left with a kind of easier to comprehend polynomial, and this is something that we can factor. It's in a quadratic form that's factorable, and it simply factors down to y minus 3 times y minus 2. And at this point now, we're going to take our x cubed and substitute it back in. And so we have x cubed minus 3, x cubed minus 2. There's nothing more we can do. These 3 is not a perfect cube, neither is 2 a perfect cube, so we can't use the difference of cubes method to factor these any more than they already are. Let's look at one other case. The final case of our factoring. First thing we do, look for a common factor. There's a common factor here across all of them. We have the m squared term that we can pull out, so that's the very first thing we'll do. Now, we recognize, or the thing to look at is that we have this m squared term, and we have an m to the 4th term. So 4 is twice of 2, so possibly we can use this quadratic form method. Just like over here, we had x to the 6th, which was twice x to the 3rd, or I mean the exponent 6 is twice of 3. The exponent here, 4, is twice of 2, so that lets us think that perhaps we can use the quadratic form. And again, indeed we can. The 36 is also a perfect square, so we can write this as 6m squared squared. So 36m to the 4th is a perfect square. We can rewrite that as 6m squared all squared. And then we can rewrite 12m squared as 2 times 6m squared. So then we say let y is equal to 6m squared, and then we can rewrite this in a way that's easier again to comprehend. Y squared plus 2y plus 1, and we could factor this now. We have our y plus 1 times y plus 1, and now we substitute back in. We take the 6m squared and put it back into wherever we see the y. And then, because we could simplify this one more step, or it's not simplifying, it's just rewriting this in a more efficient way, m squared times the quantity 6m squared plus 1, all of that squared. And this is our final factored form. There's nothing more we can do. So in summary, we've looked at 4 different ways to factor. First thing to always do is look for a common factor to pull out. Then after that, you just have to look at it to see if whether you see a special pattern, whether you see 4 terms that you can group together, or whether you see a quadratic with 3 terms where 2 of the terms have a relationship where the exponent of one of them is twice the exponent of the other. Then it's possible that you can use the quadratic form. Okay, that completes our lesson for today.